Right now, the generative AI boom is speeding toward a physical wall. We are drawing so much power to train massive language models that we are literally maxing out our data centers and electrical grids. We can't solve our most complex global problems, like mapping new climate systems or discovering breakthrough drugs, by simply plugging in more traditional hardware. We are hitting the atomic limits of how small and how fast standard microchips can get. The entire tech industry is facing an urgent need for a completely new method of computation, rather than relying on incremental upgrades to the silicon we already have. The next major leap in technology will not belong to the company that builds the largest data center. It will belong to the company that breaks the fundamental bottleneck of computation itself. By 2026, Microsoft CEO Satya Nadella had directed a complete strategic pivot. He transitioned Microsoft away from being primarily a cloud computing provider and repositioned it as a platform-first empire. Instead of fighting a brutal, expensive war over standard hardware, Microsoft stepped back to build what they envision as the ultimate operating system for scientific discovery. To pull this off, they are betting their entire ecosystem on a physics theory first proposed in 1937 by an Italian theoretical physicist named Ettore Majorana. Microsoft is wagering its future on engineering a theoretical concept that its biggest competitors had explicitly avoided because it is notoriously difficult to build. To understand why this is so risky, we have to look at the industry default. Companies building quantum computers are mostly relying on brute force superconducting qubits, which are highly sensitive to temperature and easily disrupted by the slightest environmental noise. Microsoft chose a different path: topological quantum computing. Their hardware is based on Majorana fermions, a unique type of particle behavior that acts entirely differently than standard qubits. The advantage here is structural. Majorana fermions store information in non-local topological properties, meaning they hold data in the physical geometry of a knot. If a minor disturbance hits it, the structure remains intact, making the system inherently fault-tolerant. This exponential curve illustrates the payoff. In June 2026, Microsoft announced their Majorana 2 breakthrough, proving the physics worked at scale and showing a 1,000-fold improvement in reliability over previous iterations. By solving hardware stability at the physical level, Microsoft eliminates the massive energy demands and error correction overhead that currently suffocate competing quantum models. But having a stable quantum computer is largely useless if you don't have an intelligence sophisticated enough to direct it. Enter Microsoft Discovery. Released in mid-2026, this is an agentic AI, an autonomous system capable of independently designing complex experiments and feeding them directly into the quantum hardware. To power this intelligence without breaking the entire electrical grid, Microsoft developed a strategy to address the energy constraint. Through energy-aware computing, they integrate small modular reactors, compact, highly efficient nuclear power sources, directly into their infrastructure. They are actively transforming from a heavy energy consumer into an architect of modern grid efficiency. Then comes the cognitive barrier. Raw quantum outputs are essentially pages of abstract wave functions, completely unreadable by standard business leaders or researchers. This diagram shows how Microsoft solves that problem. They use Copilot as a last-mile translator. It takes those chaotic wave functions on the left and converts them into actionable human business logic, readable charts, and text summaries on the right. Finally, they secure their market position through ecosystem lock-in. Microsoft provides open-source quantum programming libraries, like Q# for free. This invites global talent to build on their specific framework, turning it into the de facto standard for developers. Microsoft is constructing a self-sustaining ecosystem. The energy powers the AI directs the quantum hardware, the cognitive layer translates the results, and the open-source libraries keep the developers locked in. Every layer reinforces the others. We are now entering a critical crossover period between 2026 and 2031. This is the window where the brute force quantum models and Microsoft's topological approach will finally clash at a commercial scale. This timeline graph illustrates the financial stakes of that clash. The top line shows the high operational costs of brute force models. The bottom line tracks the Mariana approach. If Microsoft scales their machine by 2029 as roadmapped, their costs drop sharply. crossing the threshold and rendering the competing brute force models financially obsolete. The societal impact of winning this race is immense. The winner will unlock immediate exponential breakthroughs in mapping complex proteins for medicine, optimizing national energy grids, and simulating reactions for climate restoration. The company that navigates this 5-year transition successfully will control the foundational infrastructure of global scientific advancement for decades. This massive orchestration of physics, AI, and energy traces back to Nadella's core operating philosophy of technological humanism. His goal is to build automated systems that amplify human potential, rather than isolate or replace it. Microsoft's playbook reveals that long-term technological dominance rarely comes from isolated hardware stunts. It comes from elegant, scientifically sound concepts integrated into frictionless, reliable ecosystems. Microsoft is securing every level of the discovery process: the energy, the intelligence, and the hardware. If they successfully bridge the gap to 2031, they will have constructed the foundational layer that global science will build upon for the next 50 years.